Deep space exploration relies heavily on advanced propulsion technologies, which are crucial for enabling spacecraft to travel vast distances beyond our solar system. One prominent technology currently being researched is ion propulsion, which operates by using electric fields to accelerate ions, creating thrust. This method is known for its efficiency, consuming less fuel compared to traditional chemical rockets, making it ideal for long missions. Another exciting development is solar sails, which utilize the pressure of sunlight for propulsion. By harnessing photons, these sails can potentially allow spacecraft to travel at high speeds over extended periods, creating possibilities for missions to the outer planets and beyond. Furthermore, there is significant interest in nuclear thermal propulsion, which uses heat from a nuclear reactor to heat a propellant like hydrogen, producing thrust. This concept promises to reduce travel time to Mars and other destinations, as it provides a greater specific impulse than conventional chemical propulsion. Researchers are also exploring advanced concepts like fusion propulsion, which would harness the energy from nuclear fusion reactions. Although still in the theoretical stage, if successful, fusion propulsion could revolutionize space travel, allowing for rapid journeys across the solar system and potentially even to nearby star systems. Additionally, the concept of antimatter propulsion is being studied, where antimatter particles collide with matter to release massive amounts of energy. This method could provide extremely high speeds, but it presents significant challenges in terms of production and storage of antimatter. Another noteworthy propulsion technology is the concept of beamed energy propulsion, where energy is transmitted from Earth or a satellite to a spacecraft using lasers or microwaves. This technology could allow for lightweight spacecraft to be propelled without carrying large amounts of fuel, making deep space missions more feasible. As we think about the future of propulsion technologies, the development of electric propulsion systems like Hall effect thrusters is also gaining traction. These systems are already being used on several satellites and spacecraft, proving their reliability and efficiency for long-dimension missions. In addition, the potential of using asteroid resources for inside resource utilization is being explored, which could provide fuel for spacecraft on long journeys, reducing the need to launch everything from Earth. Moreover, advancements in materials science are playing a significant role, as lightweight and durable materials are essential for building spacecraft that can withstand the harsh conditions of space while maximizing fuel efficiency. As technology progresses, the integration of artificial intelligence in navigation and propulsion systems is also becoming a reality, allowing for more autonomous and efficient spacecraft operations, which is especially important for long-duration missions where human intervention may be limited. Deep space exploration, an exciting frontier of scientific inquiry, has several primary goals that spur the development of advanced propulsion technologies. One of the main objectives is to better understand the origins of our solar system and, by extension, the universe. This involves sending spacecraft to distant planets, asteroids, and comets, where they can gather data about their composition, structure, and the conditions that led to their formation. For instance, missions to the outer planets like Jupiter and Saturn require spacecraft to travel vast distances, often taking years to reach their targets, which emphasizes the need for propulsion systems that can sustain long-during missions without the need for frequent refueling. Another key goal is the search for extraterrestrial life, which drives missions to Mars, Europa, and Enceladus, where scientists believe subsurface oceans may harbor conditions suitable for life. To conduct thorough explorations of these intriguing worlds, advanced propulsion technologies become essential, enabling spacecraft to travel faster and more efficiently, thus reducing travel time and increasing the feasibility of returning samples to Earth. The development of technologies such as ion propulsion and solar sails is crucial in achieving these goals, as they can provide the necessary thrust while using less fuel than traditional chemical rockets. Additionally, deep space exploration seeks to expand our understanding of fundamental physics and the mechanisms behind cosmic phenomena. For instance, studying the gravitational forces at play in the outer reaches of the solar system, or observing cosmic radiation and dark matter, requires missions that can reach destinations far beyond the capabilities of current propulsion systems. As we push the boundaries of our solar system, advanced propulsion technologies such as nuclear, thermal propulsion, or even theoretical concepts like warp drives become pivotal in enabling humanity to conduct these ambitious scientific endeavors. Moreover, the exploration of other celestial bodies, including asteroids, is driven by the potential for mining resources, which could support future space missions and even life on Earth. The ability to reach and investigate these bodies efficiently without excessive travel time and energy consumption is paramount, and thus the advancement of propulsion technologies plays a critical role in ensuring we can tap into these potential resources. Finally, human exploration of Mars and beyond is a significant goal of deep space exploration. As we prepare for crewed missions to other planets, we need propulsion systems that are not only capable of transporting astronauts safely, but also able to support life-sustaining technologies during long journeys. The challenges of radiation exposure, life support, and psychological well-being of astronauts add complexity to the need for advanced propulsion technologies. Traditional propulsion systems, particularly chemical rockets, have undergone significant evolution, especially in the context of deep space missions, as strive to overcome the immense challenges posed by the vast distances and harsh environments of outer space. Initially, chemical rockets, which rely on the rapid combustion of propellants to produce thrust, were the backbone of space exploration, enabling missions like the Apollo program to the Moon and the Space Shuttle program, which enabled regular access to low Earth orbit. However, as the goals of space exploration expanded to include destinations such as Mars, the outer planets, and even interstellar space, the limitations of chemical propulsion became increasingly apparent, necessitating advancements in technology and techniques. One of the key evolutions in chemical rockets has been the development of more efficient engine designs, including the use of staged combustion cycles, which allow for higher performance by maximizing the energy extracted from the propellants. This technology was notably utilized in the Space Launch System, or SLS, which is designed to support deep space missions. Moreover, the introduction of new propellant combinations, such as liquid oxygen and methane, has provided higher efficiency and cleaner combustion, making rockets not only more powerful, but also more environmentally friendly. In addition to these improvements, hybrid rocket systems have emerged, combining solid and liquid propellants to capitalize on the strengths of both types. These hybrid systems offer greater control over thrust and can be more easily shut down or throttled, which is particularly advantageous for missions requiring precise maneuvering in deep space. The successful tests of hybrid technologies demonstrate their potential for future exploration endeavors, allowing spacecraft to make critical adjustments during their journeys. Furthermore, the evolution of propulsion technologies has also seen the exploration of alternative systems, such as ion propulsion and solar cells, which offer significant advantages for long diminishing missions. Ion propulsion, for instance, uses electric fields to accelerate ions and generate thrust, providing a continuous but gentle push that can build up over time, making it ideal for deep space missions where minimizing fuel consumption is crucial. NASA's Dawn spacecraft, which visited the asteroid belt, successfully utilized ion propulsion to travel vast distances while using a fraction of the fuel required by traditional rockets. Solar sails, on the other hand, harness the pressure of sunlight to propel spacecraft, representing a novel approach to deep space travel. By deploying large reflective sails, these spacecraft can gain momentum from the sun's rays, allowing them to traverse the solar system without using conventional fuel. This technology, while still chemical propulsion systems, while historically significant and widely used for launching spacecraft, face several limitations when it comes to deep space exploration, creating challenges for missions aimed at distant targets. One of the primary limitations is the amount of propellant required for long-dimension missions, as chemical rockets rely on the combustion of fuel and oxidizer to produce thrust. This means that after the initial launch, any additional maneuvers in space require carrying more fuel, which can add significant weight to the spacecraft, making it less efficient for missions that may last years or even decades. The need to carry large quantities of propellant can limit the payload capacity for scientific instruments, equipment, or crewed systems, restricting the scope and scale of exploration. Additionally, the efficiency of chemical propulsion systems, often measured in terms of specific impulse, is relatively low compared to other propulsion technologies, such as nuclear thermal or electric propulsion. Specific impulse refers to the thrust produced per unit of propellant consumed. And while chemical rockets can provide powerful thrust, they burn through fuel quickly, which is not ideal for the long coast phases of deep space travel. This can lead to longer travel times, which not only increases the complexity of mission planning, but also poses risks to the spacecraft and its instruments, as extended exposure to the harsh environment of space can lead to degradation of equipment. Another limitation is the operational constraints of chemical propulsion systems in vacuum conditions. While they perform well in the atmosphere, once in space, the lack of air means that the combustion process can be less predictable. This unpredictability can make it challenging to fine-tune thrust during critical mission phases, such as orbital insertions or trajectory corrections. Moreover, the need for precise timing and control in deep space missions is crucial, as small errors can lead to significant deviations from the intended path, potentially resulting in mission failure. The thermal management of chemical propulsion systems also presents a challenge. As rockets operate, they generate significant amounts of heat, which can affect the structural integrity of the spacecraft if not managed properly. In the vacuum of space, where there is no atmosphere to disperse heat, maintaining optimal operating temperatures for engines and components becomes increasingly complex, requiring additional systems and resources that further complicate mission design. Finally, the reliance on chemical propellants poses sustainability concerns, particularly as the exploration of more distant celestial bodies becomes a priority. The finite nature of available propellant sources on Earth could limit the feasibility of long-term exploration strategies, particularly if missions require substantial amounts of fuel to be. Electric propulsion systems and chemical propulsion systems represent two distinct approaches to space travel, each with its own set of advantages and challenges, especially when we consider factors like efficiency and thrust. Chemical propulsion systems, which have been the backbone of rocket technology for decades, operate on the principle of combustion. They burn fuel, typically a combination of liquid or solid propellants, to create high-pressure gas that is expelled at high velocity, producing thrust in the opposite direction, according to Newton's third law of motion. This method can generate substantial thrust, enabling spacecraft to escape Earth's gravity quickly and to reach other celestial bodies in relatively short time frames. However, the trade-off is that chemical propulsion systems tend to consume a large amount of fuel, which limits the duration and range of missions. On the other hand, electric propulsion systems, sometimes referred to as ion or solar propulsion, work quite differently. Instead of relying on combustion, they use electrical power to accelerate ions or plasma, producing thrust. This method is much more efficient in terms of fuel consumption, as electric propulsion systems can achieve a higher specific impulse, which is a measure of how effectively a rocket uses propellant. This means that electric systems can operate for extended periods, allowing spacecraft to gradually build up speed over time, rather than relying on a quick burst of thrust. While the thrust produced by electric engines is significantly lower than that of chemical engines, this lower thrust can be offset by the fact that they can run for much longer periods, gradually increasing the spacecraft's velocity to reach high speeds, perfect for long-duration missions such as those venturing to the outer planets. Moreover, the efficiency of electric propulsion systems allows spacecraft to carry less fuel, which means they can have a smaller launch mass, potentially reducing launch costs. A prime example of this technology is the Dawn spacecraft, which successfully used ion propulsion to explore the asteroid belt. Its engines allowed it to navigate and change orbits efficiently, showcasing the potential of electric propulsion for deep space exploration. While chemical propulsion remains essential for initial launches and quick maneuvers, electric propulsion is gaining traction for long-term missions, where efficiency and fuel economy are crucial. In summary, the key difference lies in the way these systems generate thrust, with chemical propulsion being more suitable for immediate, high-thrust needs, whereas electric propulsion excels in efficiency over extended periods, making it ideal for missions that require gradual acceleration and high fuel efficiency. As technology continues to advance, we might see even more innovative combinations of these. Electric propulsion systems are becoming increasingly popular for space missions due to their efficiency and ability to provide continuous thrust over extended periods. One of the main types of electric propulsion systems is ion propulsion, which works by ionizing a propellant, typically xenon, and using electric fields to accelerate these ions, producing thrust. This type of propulsion is highly efficient as it can achieve high specific impulse, which means it can use less fuel over a long duration, making it ideal for deep space missions such as NASA's Dawn spacecraft, which explored the asteroid belt. Another type is Hall effect thrusters, which are similar to ion thrusters, but utilize a magnetic field to trap electrons, creating ions from the propellant gas. This system is also known for its efficiency and has been used in various satellites and missions, including the European Space Agency's Bepi-Colombo mission to Mercury. The technology is gaining traction for its ability to provide significant thrust while consuming less power, allowing for longer missions without the need for frequent refueling. Then there are plasma propulsion systems, which, like ion and Hall effect thrusters, utilize electric fields to accelerate charged particles. However, plasma propulsion can operate with a variety of propellants, and the technology is still under development. One of the exciting aspects of plasma propulsion is its potential for very high speeds, which could revolutionize how we approach space travel, especially for missions beyond our solar system. Next, we have the electrospray thrusters, which use electric fields to accelerate tiny droplets of a liquid propellant, and they are particularly well suited for small satellites or CubeSats. These systems can provide fine control for attitude adjustments and station-keeping maneuvers, making them essential for maintaining satellite positions and orientations in orbit. Finally, there are radio frequency ion thrusters, which use radio waves to ionize the propellant gas and generate thrust. While still in the experimental phase, these systems promise to combine the benefits of existing technologies, potentially leading to even more efficient propulsion methods. As research continues, we can expect to see advancements in electric propulsion systems, contributing to the future of space exploration, making it possible to reach further destinations more efficiently, and opening new frontiers for humanity in the cosmos. Ion propulsion, a technology that has been gaining momentum in recent years, significant role in the future of deep space missions due to its unique advantages over traditional chemical propulsion. Unlike conventional rockets that rely on burning fuel to produce thrust, ion propulsion systems generate thrust by accelerating ions, which are charged particles, using electric fields. This method allows for much higher efficiency, meaning that spacecraft can achieve greater speeds while using far less fuel, making it particularly suitable for long-duration missions where every ounce of fuel savings counts. One of the key aspects of ion propulsion is its ability to provide a continuous, low-thrust acceleration over extended periods. This is in stark contrast to chemical rockets, which deliver high thrust for a short duration, but require more frequent refueling. For example, NASA's Dawn spacecraft, which utilized ion propulsion, was able to travel to the asteroid belt, visiting Vesta and Ceres thanks to its efficient use of fuel, allowing it to operate for several years without a significant need to restock. This capability opens up new possibilities for exploring distant worlds, as spacecraft can gradually build up speed, reaching higher velocities than traditional methods could offer. Furthermore, ion propulsion systems, like the ones being developed by NASA and other space agencies, utilize xenon gas as a propellant, which is abundant and easy to store. This means missions could potentially be designed to travel further into the solar system, or even beyond, as the efficiency of ion propulsion allows for more ambitious goals, such as crewed missions to Mars or exploratory missions to the outer planets and their moons, which may harbor conditions suitable for life. Another exciting aspect of ion propulsion is its potential for deep space missions that require precision maneuvering. As we look towards sending spacecraft to explore the icy moons of Jupiter, such as Europa or the distant Kuiper belt where objects like Pluto reside, the ability to make small adjustments to a spacecraft's trajectory with minimal fuel consumption is invaluable. This precision is crucial for tasks like orbit insertion around distant celestial bodies, where any miscalculation could lead to mission failure. In addition, ongoing advancements in ion propulsion technology could lead to even more powerful systems, such as the development of Hall effect thrusters, which have shown promise in increasing thrust levels. These advancements could eventually lead to spacecraft capable of carrying larger payloads, or even enabling human missions deeper into space, opening the door to new scientific discoveries and the potential for future colonization of other planets. Moreover, ion propulsion Hall effect thrusters, which are a type of electric propulsion system, play a significant role in enhancing the efficiency of spacecraft propulsion, and their operation is based on the interaction between electric and magnetic fields. This unique technology enables spacecraft to achieve higher specific impulses compared to traditional chemical rockets, allowing them to travel further and faster with less propellant. In essence, the Hall effect thruster uses a stream of ionized gas, or plasma, which is created by ionizing a propellant, typically xenon, within a chamber. Once the gas is ionized, the positively charged ions are accelerated by electric fields while electrons are confined by magnetic fields, creating a thrust that propels the spacecraft forward. One of the key advantages of Hall effect thrusters is their remarkable fuel efficiency. The specific impulse, which measures the efficiency of rocket propellants, can be significantly higher in Hall effect thrusters, often exceeding 3,000 seconds, compared to chemical rockets that typically range from 300 to 450 seconds. This means that spacecraft equipped with Hall effect thrusters can operate for longer periods using less propellant, which is particularly beneficial for long-dimension missions, such as those exploring distant planets or asteroids. Furthermore, the lower mass of the propellant required can lead to a reduction in launch costs, which is a critical factor for space agencies and private companies alike. Another reason for the increased efficiency of Hall effect thrusters is their ability to provide continuous thrust over extended periods. Unlike chemical rockets, which produce a large amount of thrust for a short burst, Hall effect thrusters can operate for hours, days, or even months, steadily accelerating the spacecraft. This allows for gradual changes in velocity, enabling precise maneuvers and more efficient trajectories. By continuously adjusting the spacecraft's speed and direction, mission planners can optimize their paths through space, taking advantage of gravitational assists and minimizing fuel consumption. Moreover, Hall effect thrusters generate significantly less waste heat compared to traditional propulsion systems. which means that the thermal management of the spacecraft is simpler and more efficient. This aspect not only improves the overall design and operation of the spacecraft, but also contributes to the longevity and reliability of the propulsion system itself. As a result, many modern spacecraft, including those used for satellite positioning, deep space exploration, and scientific missions, are increasingly adopting Hall effect thruster technology, recognizing its advantages in terms of both efficiency and performance. In addition to their application in propulsion systems, Hall effect thrusters also contribute to innovations in satellite electric propulsion, has made remarkable strides in recent years, significantly enhancing our capability for long-derivative space missions. And the technology primarily revolves around the use of solar panels to generate electricity, which powers ion thrusters, allowing spacecraft to achieve high efficiency and extended operational lifetimes. One of the most notable advancements is the development of more efficient solar arrays, which can harness sunlight more effectively, even in the distant regions of the solar system where sunlight is weaker. For instance, NASA's solar electric propulsion, which has been in the spotlight for its potential to power deep space missions, utilizes advanced solar panels that can convert a higher percentage of sunlight into usable energy, enabling spacecraft to operate longer and travel farther. In addition to improved solar arrays, advancements in ion propulsion technology have also played a crucial role in enhancing solar electric propulsion systems. The latest ion thrusters, such as NASA's evolutionary xenon thruster, are designed to provide a higher thrust-to-weight ratio, which not only increases the efficiency of the propulsion system, but also allows for quicker maneuvers and adjustments during long missions. These thrusters work by using electricity to ionize a propellant, typically xenon gas, and then accelerating the ions through electric fields, which produces thrust. The efficiency of ion thrusters is significantly higher than traditional chemical rockets, which means that spacecraft can carry less fuel and rely more on solar power, reducing the overall weight and cost of missions. Another advancement is the integration of these systems with advanced power management and thermal control technologies. These innovations ensure that solar electric propulsion systems can maintain optimal performance even when exposed to the harsh conditions of space, such as extreme temperatures and radiation levels. For example, thermal protection systems have been developed to shield solar panels and thrusters from damaging heat, while power management systems help to balance energy generation and consumption, optimizing the spacecraft's overall performance. Moreover, advancements in material science have led to the development of lighter, more durable materials for solar panels and thrusters, which not only enhance the efficiency of the propulsion system, but also contribute to the overall longevity of the spacecraft. High-efficiency solar cells made from materials like gallium arsenide have shown promise in providing superior performance compared to traditional silicon cells, and these cells are now being tested for use in future space missions. As we look towards the future, ongoing research is focused on hybrid propulsion systems that combine solar electric propulsion with other technologies, such as nuclear thermal propulsion, to further extend nuclear thermal propulsion, a technology that utilizes a nuclear reactor to heat a propellant, typically hydrogen, offers significant advantages in performance compared to conventional propulsion systems, which primarily use chemical reactions to generate thrust. One of the most notable differences is in the specific impulse, a measure of how effectively a rocket uses propellant. Nuclear thermal propulsion can achieve specific impulses of around 800 to 900 seconds, whereas conventional chemical rockets typically have specific impulses in the range of 300 to 450 seconds. This means that nuclear thermal engines can produce more thrust for a longer duration, enabling spacecraft to travel farther into space, potentially reaching destinations like Mars in a much shorter time frame. In terms of thrust-to-weight ratio, however, conventional propulsion systems often hold an advantage. Chemical rockets can produce a high amount of thrust quickly, making them suitable for lifting payloads off the Earth's surface, where overcoming gravity is crucial. Nuclear thermal engines, while efficient in space, require a different approach during launch, as they are not designed to operate in the dense atmosphere and need to be integrated with traditional launch systems. When considering safety, nuclear thermal propulsion presents unique challenges. The primary concern involves the handling and potential release of radioactive materials. If a nuclear thermal engine were to malfunction during launch, the consequences could be severe. However, advancements in reactor design and safety protocols have been developed to minimize these risks. For example, many modern designs focus on passive safety features, which would allow the reactor to cool down without external intervention in case of an emergency. In contrast, conventional propulsion systems, while generally safer in terms of immediate risks, can also pose hazards, such as the potential for explosive failures during launch. Furthermore, the environmental impacts of chemical propellants, which produce greenhouse gases and other pollutants, are an ongoing concern, whereas nuclear thermal propulsion, when functioning correctly, produces only heat and vapor as exhaust, offering a cleaner alternative in terms of emissions. Moreover, the operational life of nuclear thermal engines can be significantly longer than that of chemical engines, which often require more frequent maintenance and replacement. This longevity can contribute to mission success, especially for long derivative space missions where reliability is critical. The debate over which propulsion method is superior often hinges on mission profiles. For missions requiring rapid acceleration and high thrust, such as launching payloads from Earth, chemical rockets remain the preferred choice. However, for deep space exploration, where efficiency and long-term performance are paramount, nuclear thermal propulsion could provide the necessary capabilities to. Nuclear electric propulsion, often referred to as NEP, presents a fascinating and innovative approach to deep space travel, with several potential benefits that could revolutionize our exploration of the cosmos. One of the most significant advantages of NEP is its ability to provide continuous thrust over long periods, which is a stark contrast to conventional chemical propulsion systems that burn fuel quickly and provide only short bursts of power. This continuous thrust means that spacecraft utilizing nuclear electric propulsion can gradually build up speed, allowing them to reach much higher velocities over time, which is particularly advantageous for missions to distant destinations such as Mars or even the outer planets of our solar system, where traditional propulsion would take much longer. Another important benefit of nuclear electric propulsion is its efficiency. NEP systems can convert nuclear energy into electrical power, which can then be used to drive ion or Hall effect thrusters, technologies that are known for their high specific impulse, or fuel efficiency. This efficiency translates into the spacecraft needing less propellant for the same journey, which not only reduces the overall mass of the spacecraft, but also significantly lowers launch costs. Furthermore, this reduced reliance on chemical propellants opens up new possibilities for spacecraft design, allowing for more complex missions that can carry additional scientific instruments or payloads, ultimately enhancing our ability to conduct research in space. Additionally, nuclear electric propulsion can enable longer directory propulsion, can support various onboard systems, including life support, communication, and scientific instruments. This capability is crucial for missions that may take several years or even decades, as it allows for a stable and reliable source of energy throughout the entire journey, without the need for frequent resupplies or refueling, which would be logistically challenging for missions beyond low Earth orbit. Moreover, NEP can significantly reduce travel time to outer planets or other celestial bodies, which can be vital for crewed missions. For instance, a mission to Jupiter with a conventional chemical rocket could take several years, whereas with nuclear electric propulsion, the journey could be shortened to a matter of months. This reduction in travel time not only decreases the amount of time astronauts spend in space, minimizing their exposure to harmful cosmic radiation, but also allows for more efficient use of time for scientific research and exploration once they arrive at their destination. The technology behind nuclear electric propulsion is also advancing rapidly, with recent developments in reactor design and materials that promise to enhance safety and efficiency further. For example, research into nuclear thermal propulsion, which utilizes an in situ resource utilization, often abbreviated as ISRU, refers to the practice of harnessing and using resources found on site in space rather than relying solely on materials launched from Earth, which can be both costly and complex. When it comes to deep space missions, ISRU has the potential to significantly transform propulsion technologies, creating a more sustainable and efficient means of travel beyond our planet. For instance, one of the most exciting applications of ISRU is the extraction of water from lunar or Martian soil, which can be split into hydrogen and oxygen through a process known as electrolysis. This hydrogen and oxygen can then be used as propellant for rockets, allowing missions to refuel on site rather than having to carry all the fuel from Earth. This means spacecraft could potentially travel farther and stay longer, as they wouldn't have to return to Earth for refueling. Moreover, ISRU can lead to the development of new propulsion technologies, such as hybrid systems that combine traditional chemical propulsion with other methods, like ion propulsion or nuclear thermal propulsion. By leveraging local resources, these hybrid systems can become more efficient, using the energy derived from the extraction and conversion of Martian or lunar materials to enhance thrust and efficiency. For example, if a mission to Mars can produce methane from carbon dioxide in the Martian atmosphere, this methane can be used as fuel, in combination with oxygen sourced from local ice. This not only reduces the mass of the payload that must be launched from Earth, but also opens up new possibilities for longer dimension missions, as spacecraft can carry out complex maneuvers and sustain life support systems using locally sourced materials. Additionally, ISRU could lead to innovations in propulsion that make use of exotic materials found in space, such as helium-3, which is relatively abundant on the Moon. Helium-3 is considered a potential fuel for future fusion reactors, which could provide a nearly limitless source of energy. In theory, if we can develop fusion propulsion using helium-3, deep space travel could become faster and more efficient, allowing humanity to explore the outer planets and beyond with unprecedented speed. The ability to harvest these resources not only supports the mission itself, but also lays the groundwork for future colonization efforts, as establishing a human presence on other celestial bodies will require sustainable energy and fuel sources. Furthermore, ISRU can help to reduce the costs associated with launching missions, as less cargo means lower launch weights, and therefore smaller rockets can be used. This could lead to additive manufacturing, often known as 3D printing, is revolutionizing various fields, including aerospace, and it plays a particularly crucial role in the development of propulsion systems for deep space exploration. By enabling the creation of complex components that were previously difficult or even impossible to manufacture using traditional techniques. This innovative approach allows engineers to design and produce parts with intricate geometries, which can lead to lighter, more efficient propulsion systems, essential for deep space missions, where weight savings can significantly impact fuel efficiency and overall mission success. For instance, NASA has been exploring the use of additive manufacturing to create rocket engine components, such as injectors and combustion chambers, which can be optimized for performance and reliability while reducing manufacturing time and costs. One of the remarkable advantages of additive manufacturing is its ability to produce parts on demand, which can be especially beneficial for missions that are far from Earth, where resupply missions are not feasible. This capability allows engineers to tailor components to specific mission requirements, and even make adjustments in real time based on performance data gathered during a mission. For example, the development of the RS-25 engine, which is being used in the Space Launch System, has incorporated 3D printed parts, demonstrating how this technology can enhance traditional rocket propulsion systems, making them more adaptable and efficient. Moreover, additive manufacturing supports the use of advanced materials such as high-strength alloys and composites which can withstand the extreme conditions of space travel. These materials can be layered and fused during the printing process, resulting in parts that not only meet the stringent requirements of deep space exploration, but also exhibit enhanced thermal resistance and durability. This is particularly important for propulsion systems, which face intense heat and pressure during launch and operation. In addition to creating individual components, additive manufacturing can also streamline the entire supply chain for propulsion systems. Instead of relying on multiple suppliers for various parts, manufacturers can produce many components in-house, reducing lead times and increasing the overall efficiency of the production process. This is critical for deep space exploration, where every second counts and delays can have significant consequences for mission timelines. Furthermore, as space agencies and private companies look to establish a human presence on Mars and beyond, the ability to manufacture components on site using local materials becomes increasingly important. This concept, known as in-situ resource utilization, can be complemented by additive manufacturing, allowing explorers to create necessary parts and systems using resources found on other celestial bodies, thus reducing the need to transport everything from Earth. Advanced materials play a crucial role in the design and efficiency of propulsion technologies, especially in the context of space exploration, where the extreme conditions demand innovative solutions. Materials like lightweight composites, ceramics, and advanced alloys are being utilized to enhance the performance of propulsion systems, making them more efficient and capable of withstanding the harsh environments of space. For instance, the use of carbon fiber reinforced polymers allows for the creation of lighter structures, which in turn reduces the overall mass of spacecraft, enabling them to carry more payload or achieve higher velocities with the same amount of thrust. Furthermore, advanced thermal protection materials, such as aerogels and high-temperature ceramics, are essential for engines that need to operate at extreme temperatures, ensuring that components do not fail under intense heat generated during propulsion. In rocket engines, the choice of materials directly affects the efficiency of fuel combustion. For example, superalloys, which are designed to resist deformation at high temperatures, are critical in the turbines of rocket engines, allowing them to operate at peak performance without compromising structural integrity. This leads to better fuel efficiency as engines can convert more of the fuel's energy into thrust. Additionally, the development of advanced propellant materials, like those based on hybrid or composite fuels, can further enhance the performance of propulsion systems. These new propellants can burn at higher temperatures and pressures, providing more thrust and reducing the amount of fuel required for a successful launch. Moreover, advancements in additive manufacturing, often referred to as 3D printing, allow for the creation of complex engine components that were previously difficult or impossible to manufacture with traditional methods. This technology not only enables the production of lighter, more efficient parts, but it also allows for rapid prototyping and testing of new designs, speeding up the development process of propulsion technologies. For example, NASA and other space agencies have successfully created rocket engine components using 3D printing, which has significantly reduced the production costs and time needed for testing. The integration of smart materials, which can change properties in response to external stimuli, is also making waves in propulsion technology. These materials can adapt to environmental changes, potentially allowing for more versatile and adaptive propulsion systems that could optimize performance based on specific mission profiles. For instance, materials that can alter their stiffness or shape in response to temperature changes could improve the efficiency of control surfaces on spacecraft, leading to better maneuverability and stability during flight. Overall, the influence of advanced materials on propulsion technologies is profound, leading to innovative designs that enhance efficiency, reliability. In the quest to send humans to Mars, researchers and engineers are exploring a variety of emerging propulsion technologies, each with the potential to drastically reduce travel time and improve mission efficiency. One of the most promising concepts is nuclear thermal propulsion, which utilizes a nuclear reactor to heat a propellant, usually hydrogen, to extremely high temperatures, allowing it to expand and be expelled through a rocket nozzle, generating thrust. This method could potentially cut the travel time to Mars to around 3 to 4 months, compared to the 6 to 9 months required by conventional chemical rockets. Additionally, there is interest in nuclear electric propulsion, where a nuclear reactor generates electricity that powers ion thrusters. These thrusters work by accelerating ions using electric fields, providing a continuous, albeit low-thrust, propulsion that could be ideal for long-dimension space missions, allowing spacecraft to gradually build up speed over time. Another area of research is around solar sails, which harness the pressure of sunlight for propulsion. Using large reflective sails, these spacecraft can gradually accelerate as they catch sunlight, making them fuel-efficient for long-distance travel. Though the technology is still in its infancy, missions like the Planetary Society's Light Sail project have demonstrated the feasibility of this concept in low Earth orbit, and future missions could explore its applications for Mars exploration. Furthermore, there are advancements in advanced chemical propulsion systems, including hypergolic propellants, which ignite on contact and can offer greater reliability for landing and takeoff from Mars' surface. Another intriguing technology under study is the use of plasma propulsion, particularly the VASIM MIR, or Variable Specific Impulse Magnetop rocket, which uses radio waves to ionize and heat a gas, creating plasma that is then expelled to produce thrust. This technology promises a high specific impulse, which means it can produce a lot of thrust relative to the amount of propellant used, making it suitable for long missions where efficiency is critical. Additionally, researchers are looking into the potential of using in situ resource utilization, or ISRU, which involves producing fuel from resources found on Mars itself, such as extracting oxygen from the Martian atmosphere or using water ice for fuel, thereby reducing the amount of propellant that needs to be carried from Earth. As humanity's understanding of space travel evolves, the integration of these emerging propulsion technologies could pave the way for more ambitious missions, not only to Mars, but also to other destinations in our solar system. Each of these technologies has its own benefits and challenges. An ongoing research, antimatter propulsion, a concept that sounds like it's straight out of a science fiction novel, holds the potential to revolutionize deep space exploration in ways we are only beginning to understand. To grasp how this technology could reshape our journey into the cosmos, it's essential to first comprehend what antimatter is. Antimatter is essentially the mirror image of regular matter, composed of antiparticles that have the same mass as particles of ordinary matter, but with opposite charges. When matter and antimatter come into contact, they annihilate each other, releasing an immense amount of energy, far more than conventional rocket fuels can provide. This energy release is governed by Einstein's famous equation, E equals mc2, which illustrates how a tiny amount of mass can produce a massive amount of energy. In practical terms, if we could harness even a small quantity of antimatter, the energy produced would be enough to propel a spacecraft at unprecedented speeds. One of the most exciting prospects of antimatter propulsion is its potential for interstellar travel, enabling missions to other star systems, which, with current technology, would take thousands of years. Antimatter engines could theoretically reduce travel time to mere decades, opening up possibilities for human exploration beyond our solar system. Imagine a spacecraft reaching Alpha Centauri, our closest neighboring star system, within a human lifetime, allowing us to gather data about potentially habitable exoplanets and perhaps even send back images and samples, forever changing our understanding of the universe. Additionally, antimatter propulsion systems could operate with remarkable efficiency, allowing spacecraft to carry less fuel, which means more room for scientific instruments, crew, and supplies. The ability to travel farther and faster could facilitate missions to the outer planets, the Kuiper Belt, and beyond, where we could investigate the origins of our solar system and the building blocks of life. The implications for scientific discovery are enormous, as we could explore celestial bodies that are currently unreachable with our existing propulsion technologies. However, the development of antimatter propulsion comes with significant challenges. Producing antimatter is incredibly expensive and difficult. Currently, we can only create tiny amounts in particle accelerators, and the cost of creating just 1 gram of antimatter is estimated to be around $62.5 trillion. This raises questions about the practicality of producing antimatter for propulsion, and the infrastructure required to store and handle it safely poses additional hurdles. Antimatter must be contained in a vacuum to prevent it from coming into contact with regular matter, which developing practical antimatter propulsion systems presents a multitude of challenges, starting with the fundamental nature of antimatter itself, which, while incredibly efficient as a potential fuel source, is notoriously difficult to produce and store. Antimatter is created in minuscule amounts in particle accelerators, and the production process requires vast amounts of energy, making it an expensive endeavor. For instance, to produce just 1 milligram of antimatter, it is estimated that it would cost around $62.5 trillion. A staggering figure that highlights the economic hurdles in harnessing this technology. Once produced, the next significant challenge is storage, as antimatter annihilates upon contact with regular matter, releasing immense energy in the process. Current storage methods often involve magnetic or electric fields to keep antimatter suspended in a vacuum, preventing it from touching the walls of its containment vessel. But these methods are not yet practical for large applications or long-term usage. The engineering requirements for maintaining such a system are complex and still in the experimental phase, leaving many questions about scalability and safety. Moreover, the efficiency of antimatter as a propulsion system hinges on the ability to manage the reactions that occur when antimatter meets matter. When antimatter interacts with matter, it produces gamma rays and other particles, and this requires advanced systems to handle the energy output and convert it into thrust effectively. Currently, the technology to convert the energy from these reactions into usable propulsion is theoretical, and practical designs are still in the conceptual stage. In addition, there are significant safety concerns associated with antimatter propulsion. A small amount of antimatter, when it comes into contact with matter, can cause catastrophic explosions. This poses risks not only for spacecraft carrying antimatter, but also for the environments in which they are launched and operated. The regulatory and safety protocols for handling such volatile materials are still under development, and would need to be rigorously established before any serious implementation could occur. Furthermore, the long-term effects of exposure to radiation produced by antimatter reactions must be studied, as the gamma rays generated can be harmful to both equipment and human life. Understanding the biological impacts and ensuring the safety of crewed missions are paramount concerns that contribute to the complexity of developing antimatter propulsion systems. Finally, there are also challenges related to the political and ethical considerations surrounding the use of antimatter. The potential for using antimatter in military applications raises questions about the regulation and control of such powerful technology, while the financial investment required to develop practical antimatter propulsion, plasma propulsion technology, represents a fascinating advancement in the field of space exploration, utilizing the fundamental properties of plasma, which is often referred to as the fourth state of matter, alongside solids, liquids, and gases. Plasma consists of ionized gas, where the atoms have been energized to the point that electrons are stripped away, resulting in a mixture of ions and free electrons. This unique composition allows plasma propulsion systems, such as ion thrusters and Hall effect thrusters, to generate thrust in a very efficient manner. In essence, these systems work by accelerating charged particles, typically ions, through electric fields, which then expel them at high speeds, producing a reaction force that propels the spacecraft in the opposite direction, according to Newton's third law of motion. One of the most notable features of plasma propulsion is its remarkable fuel efficiency, which is measured in terms of specific impulse, a measure of how effectively a rocket uses propellant. Plasma thrusters can achieve significantly higher specific impulse than traditional chemical rockets, meaning they can use less fuel to produce the same amount of thrust over extended periods. This efficiency is particularly beneficial for long-duration missions, where carrying large amounts of fuel becomes impractical. The high exit velocity of ions allows spacecraft to gradually build up speed over time, rather than relying on short, powerful bursts of thrust, which is the hallmark of chemical propulsion systems. The potential applications of plasma propulsion technology in deep space are vast and exciting. For instance, it could revolutionize missions to distant planets, such as Mars or even the outer planets of our solar system. The ability to travel more efficiently means that spacecraft could arrive at their destinations faster, opening the door to more ambitious exploration missions. Additionally, plasma propulsion could be used for spacecraft that require long-term operations, such as those designed for interplanetary travel or missions that involve orbiting other celestial bodies for extended periods. The ability to make continuous adjustments in trajectory and speed without the need for large amounts of fuel allows for more complex mission profiles, including those that require intricate navigational maneuvers. Furthermore, plasma propulsion technology holds promise for future human exploration of Mars, where efficient travel could make manned missions more feasible, allowing astronauts to reach the red planet with less logistical burden. Scientists are also looking at how plasma propulsion could be used in conjunction with solar sails, which harness the pressure of sunlight for propulsion, creating hybrid systems that could enable even deeper space exploration. The concept of using plasma propulsion for missions beyond our solar system is laser propulsion, a cutting-edge technology that harnesses the power of focused laser beams to propel spacecraft, holds immense promise for the future of deep space exploration, offering a novel approach that could vastly change how we reach distant worlds. At its core, this method involves ground-based lasers, or orbital lasers, directing energy towards a spacecraft which is equipped with a special sail or reflective surface that captures the light energy and converts it into thrust. This concept, often referred to as laser sail propulsion, has gained traction in scientific circles due to its potential for high speeds, allowing us to reach destinations in the solar system and beyond much more quickly than traditional chemical rockets. One of the most exciting aspects of laser propulsion is its efficiency, as it can significantly reduce the amount of fuel needed for long journeys. Unlike conventional rockets that carry their fuel on board, laser propulsion allows a spacecraft to use energy beamed from Earth or other locations, meaning that the vehicle can be lighter and more agile. This reduction in mass translates into more payload capacity, enabling missions to carry advanced scientific instruments, technology demonstrations, or even crewed missions further into the cosmos. The possibility of achieving speeds that approach a significant fraction of the speed of light, thanks to continuous laser acceleration, opens up remarkable opportunities for interstellar exploration, potentially allowing us to send probes to the nearest stars, such as Proxima Centauri, within a human lifetime. Moreover, laser propulsion systems can be designed to operate in various environments, including vacuum conditions in space and atmospheric conditions on Earth. As we develop this technology, there are various applications we can envision. For example, a laser propulsion system could help launch small satellites into orbit, or it could be used to propel larger spacecraft on missions to Mars, the outer planets, or even beyond our solar system. The concept has been explored in theoretical studies and experimental tests, with organizations like NASA and the Breakthrough Initiatives. Look at the potential for laser propulsion was highlighted in the Breakthrough Starshot Initiative, which aims to develop microscopic spacecraft capable of traveling to the Alpha Centauri system, using powerful ground-based lasers to accelerate small light sails to incredible speeds. Safety and precision are also key considerations in the development of laser propulsion. Engineers and scientists are working hard to ensure that the laser beams can be accurately aimed at the spacecraft without risk to other satellites or spacecraft in orbit. The technology must also be capable of adjusting to various conditions, such as changes in the spacecraft's trajectory or speed. Furthermore, solar sails, which harness the power of sunlight for propulsion, represent a fascinating advancement in space exploration technology, offering innovative solutions for deep space missions. The concept behind solar sails is relatively straightforward, yet profoundly ingenious. They operate on the principle of radiation pressure, which is the force exerted by light as it strikes a surface. When sunlight hits the large reflective surface of a solar sail, it transfers momentum to the sail, propelling the spacecraft forward. This method of propulsion is particularly advantageous for deep space missions, where traditional fuel sources become impractical due to the vast distances involved and the need for extensive fuel storage. One of the most compelling features of solar sails is their ability to continue accelerating over time. Unlike conventional propulsion systems that rely on burning fuel, solar sails can gradually gain speed as they absorb sunlight, which is abundant in space. As the sail moves further from the sun, it can still capture light from other stars, albeit at a reduced efficiency. The design of solar sails, which typically consists of thin, lightweight materials, allows them to be deployed to large sizes, maximizing their surface area to catch as much sunlight as possible. This makes them incredibly efficient, especially when coupled with advanced materials like mylar or kapton, which reflect a high percentage of incoming sunlight. In practical applications, solar sails have already seen some successful demonstrations, such as the Planetary Society's Light Sail project, which tested the concept in low Earth orbit. The mission showcased not only the feasibility of solar sail technology, but also its ability to control the spacecraft's orientation and trajectory using sunlight. For deep space missions, solar sails could potentially be used to travel to distant destinations, like the outer planets or even interstellar space, where they could take advantage of the constant influx of solar radiation. Additionally, solar sails offer a unique advantage in terms of mission duration and cost. Because they do not require the same amount of fuel as traditional spacecraft, missions can be designed to last for years or even decades, allowing scientists to gather data over extended periods. This longevity could be essential for exploring remote areas of the solar system, where traditional missions would require numerous resupply missions or complex logistics. Furthermore, the reduced need for fuel means that missions could be launched more economically, as the overall weight and complexity of the spacecraft can be significantly lessened. It's important to note that while solar sails hold great promise, they also present unique challenges. For instance, maneuvering a solar sail in deep space requires precise calculations, and solar sails, which utilize the pressure of sunlight to propel spacecraft, offer some intriguing advantages for interstellar travel, while also presenting a series of limitations that need to be acknowledged. One significant advantage of solar sails is their ability to harness a virtually unlimited source of energy, the sun, allowing them to accelerate over time without the need for fuel, which means that once deployed, they can continue to gain speed as long as they are in sunlight. This makes them incredibly efficient for long-term missions, especially in the vast emptiness of space, where traditional fuel-based propulsion systems would quickly deplete their resources. Another benefit is their lightweight design, which can reduce the overall mass of the spacecraft, enabling higher speeds and lower launch costs. Solar sails can also be designed to be very large, providing a greater surface area to catch sunlight, and thus they can achieve impressive velocities over time, potentially reaching a significant fraction of the speed of light, which is essential for interstellar distances. However, despite these advantages, solar sails come with limitations that cannot be overlooked. For one, their acceleration is gradual, meaning that they require a long time to reach high speeds, making them less suitable for missions that need to cover short time frames. Additionally, solar sails are highly dependent on their distance from the sun. As they travel further away from our star, the intensity of sunlight decreases, leading to a reduction in propulsion efficiency. This creates a challenge for missions heading to distant star systems, where the light from other stars is much weaker. Furthermore, solar sails are vulnerable to micrometeoroids and space debris, which can damage their delicate surfaces, potentially compromising their ability to function effectively. The orientation and tracking of the sail also require sophisticated control systems to ensure that they are positioned optimally to capture sunlight, which adds complexity to mission design and operation. Moreover, navigation becomes a challenge as the spacecraft travels away from the solar system. The lack of a strong gravitational pull from a nearby star can make it difficult to steer the sail toward a desired target. In conclusion, while solar sails present an exciting avenue for interstellar travel due to their unique propulsion method and efficient energy use, they also face significant hurdles that must be addressed. Understanding these advantages and limitations is crucial for future missions aiming to explore the stars beyond our solar system, as researchers continue to innovate and refine technologies that could one day take us on incredible journeys through the cosmos. The beamed energy propulsion system operates on a fascinating principle, where energy is transmitted from a source to a spacecraft through directed beams, typically using lasers or microwave beams. Imagine a powerful laser focusing its energy on a spacecraft that is positioned at a distance. This energy, instead of being contained within the spacecraft, is used to heat a propellant, which is then expelled to create thrust, pushing the spacecraft forward. This method allows for a lightweight design since the spacecraft does not need to carry large amounts of fuel, as the energy is beamed to it from a ground station or an orbital platform. The efficiency of this system is quite remarkable, as it reduces the weight that needs to be launched into space, which can be a significant advantage in terms of cost and engineering. Furthermore, the concept relies on the precision of the beam direction and the ability to maintain a strong connection between the energy source and the spacecraft. This requires advanced technology to track the spacecraft as it moves, ensuring that the beam remains focused on the target. Such systems can potentially provide continuous thrust, allowing for long direction missions that could reach distant planets or even travel beyond our solar system. One of the most exciting aspects of beamed energy propulsion is its potential to enable rapid acceleration, significantly reducing travel times compared to traditional chemical propulsion. For instance, when discussing missions to Mars, using beamed energy could cut down the journey time from several months to just weeks, making human exploration of the red planet far more feasible. Research is ongoing, with various experiments and simulations being conducted, aiming to refine the technology and explore its practical applications. Notably, projects like the Planetary Society's Light Sail, although primarily focused on solar sailing, hint at the future possibilities of using directed energy for propulsion, as scientists continue to push the boundaries of what we understand about space travel. This technology also opens up discussions about safety and control, as the beams must be powerful enough to propel a spacecraft, but managed carefully to avoid unintended damage to other objects in space or even to the environment on Earth, highlighting the need for responsible development of such systems. Given the complexity and novelty of beamed energy propulsion, researchers are also keen to explore the implications for energy generation and storage, envisioning a future where energy can be harnessed and transmitted across vast distances, not only for propulsion, but for other applications in space exploration. As scientists and engineers forge ahead with this groundbreaking concept, they are not only reimagining how we travel in breakthrough propulsion physics, which involves the exploration and development of new methods of propulsion that go beyond conventional rocket technologies, offers exciting possibilities for the future of space travel, fundamentally changing how we understand and traverse the cosmos. One significant implication of these advancements is the potential for faster-than-light travel, which, while still a theoretical concept, opens up discussions about the feasibility of reaching distant star systems within a human lifetime. Concepts like the Alcubierre warp drive, which suggests creating a bubble in space-time that moves faster than light, could make interstellar journeys seem less like science fiction and more like a tangible goal. Additionally, breakthroughs in propulsion technologies could lead to more efficient propulsion systems, such as ion thrusters or plasma engines, which utilize electricity to accelerate ions and create thrust, allowing for longer missions with less fuel. This efficiency could enable spacecraft to travel deeper into our solar system and beyond, making missions to Mars, the outer planets, and even the Kuiper Belt more practical and sustainable. Moreover, the implications of breakthrough propulsion physics extend to the development of new materials and technologies that could withstand the harsh conditions of space, such as extreme temperatures and radiation. Technologies like light sails, which use the pressure of sunlight to propel spacecraft, could allow for lightweight, fast-moving probes capable of reaching the outer edges of the solar system in a fraction of the time it currently takes. Furthermore, advancements in propulsion could enhance the safety and reliability of space travel, fostering a new era of exploration where human crews can undertake long-duration missions with reduced risks. Maxwell. Meet Dr. Glanville. The integration of artificial intelligence and autonomous systems in conjunction with these advanced propulsion methods could also revolutionize how we navigate and operate in space, making it possible for spacecraft to make real-time adjustments and improvements during their journeys, adapting to unforeseen challenges in the vastness of space. As scientists and engineers continue to push the boundaries of our understanding of physics, the implications of these breakthroughs could also inspire new generations of researchers and enthusiasts, driving interest and investment in space exploration. Prospect of establishing bases on other celestial bodies, such as the Moon or Mars, could become more achievable, leading to a greater human presence in space and the potential for collaboration between nations and private companies. Ultimately, the exploration of breakthrough propulsion physics could redefine our place in the universe, transforming humanity's relationship with space as we strive to explore, understand, and perhaps even inhabit worlds beyond our own, making previously unimaginable journeys a reality and ushering in a new era of discovery and adventure. Magnetic propulsion, a fascinating concept that utilizes magnetic fields to create thrust, holds great promise for deep space exploration missions, particularly because it can potentially overcome some of the limitations faced by traditional propulsion systems. The basic principle behind magnetic propulsion involves the interaction between magnetic fields and charged particles, leading to a force that can propel a spacecraft forward. One of the most notable methods of magnetic propulsion is through the use of electromagnetic sails, or e-sails, which harness solar wind, a stream of charged particles emitted by the sun. When a spacecraft, equipped with long conductive wires, is placed in the path of solar wind, the interaction with the charged particles generates thrust, allowing the spacecraft to accelerate without the need for conventional fuel. This technology could enable missions to distant planets, or even beyond our solar system, by providing a continuous source of propulsion, thus reducing the need for fuel resupply. Another innovative approach is the use of magnetoplasmodynamic, MPD, thrusters, which utilize magnetic fields to accelerate ionized gases, or plasmas, to produce thrust. Unlike chemical rockets, which rely on combustion, MPD thrusters can achieve much higher specific impulses, meaning they are significantly more efficient for long missions. This type of propulsion system could be particularly advantageous for missions to the outer planets, where traditional propulsion methods would struggle due to the vast distances and the long travel times involved. The ability to generate thrust continuously, using electricity opens up the possibility for spacecraft to travel faster and more efficiently through the solar system. Furthermore, magnetic propulsion systems could work well in conjunction with other technologies, such as solar panels or nuclear reactors, to provide the necessary energy for these advanced propulsion methods. For example, if a spacecraft were equipped with a nuclear reactor, it could generate a substantial amount of electricity to power an MPD thruster, allowing for sustained high-speed travel through the cosmos. This synergy between different power sources and propulsion methods can maximize the capabilities of a spacecraft, making it more versatile and adaptable for various deep space missions. In addition to propulsion, magnetic fields can also be used for maneuvering spacecraft in deep space. By adjusting the strength and orientation of magnetic fields, a spacecraft can change its trajectory without expending additional fuel. This precise control can be crucial when navigating around celestial bodies or making course adjustments during long missions. Researchers are actively exploring these possibilities, investigating how magnetic fields can be further manipulated to enhance spacecraft performance and efficiency. While magnetic propulsion technologies are still in the experimental stage, in recent years, scientists and engineers have been exploring various experimental propulsion technologies that hold promise for deep space applications. As traditional chemical rockets may not be the most efficient means for long-duration space missions, one of the most talked about technologies is ion propulsion, which uses electric fields to accelerate ions, creating thrust. This method is much more efficient than conventional rockets, allowing spacecraft to travel further with less fuel. NASA's Dawn spacecraft, for instance, successfully used ion propulsion to explore the asteroid belt, demonstrating how effective this technology can be for deep space missions. Another exciting avenue is the development of solar sails, which harness the momentum of sunlight to propel spacecraft. By deploying large reflective sails, spacecraft can ride the pressure of photons emitted by the sun, gradually accelerating over time. The Planetary Society's light sail mission successfully demonstrated this concept, showing not only that solar sails can work, but also that they can be a viable option for long-distance exploration. Additionally, nuclear thermal propulsion is being revisited, which involves using a nuclear reactor to heat a propellant, such as hydrogen, and then expelling it to create thrust. This technology offers a much higher specific impulse compared to conventional chemical propulsion, potentially reducing the travel time to distant destinations like Mars. NASA has been conducting tests on nuclear thermal engines, aiming to develop a reliable system that could significantly advance human exploration of the solar system. Furthermore, there's research into electromagnetic propulsion systems, such as the VASIM-R, Variable Specific Impulse Magnetic Plasma Rocket Engine. This technology uses magnetic fields to accelerate plasma, creating thrust. It can be adjusted for different missions, providing flexibility in how fast or far a spacecraft can go, depending on its needs. This adaptability could be particularly useful for missions to the outer planets or even beyond. Another innovative concept is the concept of antimatter propulsion, which, while still largely theoretical, has the potential to provide enormous amounts of energy from very small amounts of fuel. Antimatter reactions release energy on a massive scale, and if we can figure out how to produce, store, and utilize antimatter efficiently, it could revolutionize space travel, allowing us to reach distant stars in a fraction of the time it would take with current technologies. Lastly, researchers are exploring the concept of beamed energy propulsion, which involves using powerful lasers or microwaves from Earth or orbit to provide thrust to a spacecraft. This method could allow for lightweight spacecraft, as they wouldn't need to carry their own fuel. Propulsion technologies play a critical role in shaping mission design and trajectory planning for deep space exploration, as they determine how spacecraft will travel through the vast distances of space and how efficiently they can reach their destinations. The choice of propulsion system, whether it's chemical rockets, ion engines, or even emerging technologies like solar sails or nuclear thermal propulsion, directly influences the spacecraft's speed, maneuverability, and fuel efficiency. For instance, traditional chemical rockets, which rely on rapid combustion of fuel to produce thrust, are powerful and capable of lifting spacecraft off Earth's surface, but they have limitations in efficiency for long missions, often requiring substantial amounts of fuel for extended journeys. This has led mission planners to consider alternative propulsion methods for deep space missions. Ion propulsion, for example, uses electricity to accelerate ions, creating a much more efficient thrust that can be sustained over long periods. This type of propulsion allows spacecraft to gradually build up speed, enabling them to reach higher velocities than they could with conventional rockets. However, ion engines produce lower thrust, which means they take longer to reach their destination, making them suitable for missions where time is less of a critical factor, such as missions to asteroids or distant planets. The mission design must account for this, planning trajectories that optimize the spacecraft's path to take advantage of gravity assists from celestial bodies, which can provide additional speed without the need for extra fuel. In addition to the type of propulsion, the design of the mission trajectory itself is heavily influenced by propulsion technologies. For instance, missions to Mars often employ a technique called the Hohmann transfer orbit, which is the most fuel-efficient way to travel between two orbits, but it requires precise timing to launch when Earth and Mars are optimally aligned. This means mission planners must carefully calculate not just the propulsion capabilities, but also the timing of the launch, the duration of the journey, and the spacecraft's ability to perform orbital maneuvers along the way. Propulsion systems also dictate the spacecraft's ability to perform critical maneuvers, such as entering orbit around another planet, landing on its surface, or even returning to Earth. For example, the recent Mars Perseverance rover utilized a combination of propulsion technologies, including a sky crane maneuver for landing, which was essential for its delicate touchdown on the Martian surface. The design of such maneuvers relies heavily on the capabilities of the propulsion systems in place, as well as the spacecraft's mass and the gravitational influences of the celestial bodies. When considering the safety of advanced propulsion systems for crewed deep space missions, several important factors come into play, making it crucial to understand the broader implications of these technologies, as well as the specific risks they present. First, one must acknowledge that advanced propulsion systems, such as ion drives, nuclear thermal propulsion, or even potential concepts like antimatter propulsion, operate on principles that differ significantly from conventional chemical rockets, which have been used for decades. These differences can introduce unique challenges. For instance, ion drives, while efficient and capable of providing continuous thrust over extended periods, produce very low thrust levels, which means that crewed spacecraft may take longer to reach their destinations, leading to prolonged exposure to space hazards. Radiation is a paramount concern, particularly in deep space, where astronauts are exposed to higher levels of cosmic rays and solar particles, far beyond what they encounter in low Earth orbit. Advanced propulsion systems, especially those that rely on nuclear technology, would need to incorporate robust shielding to protect crew members from radiation exposure during both the operation of the propulsion system and the journey itself. Furthermore, the potential for radiation leaks from a malfunctioning nuclear reactor poses significant risk, necessitating extensive safety protocols and contingency plans. Another consideration is the reliability of these advanced systems. As they often incorporate new and untested technologies, the risk of mechanical failure increases, which can be particularly dangerous in deep space where resupply missions are not feasible. Therefore, designing propulsion systems with multiple redundancies and fail-safes is essential to ensure that the crew can maintain control and safely complete their mission, even if one component fails. Additionally, the psychological impact of long-derivative space travel cannot be overlooked. Crew members will be isolated for extended periods, and any failure or malfunction with the propulsion system could lead to heightened anxiety and stress, which could impact decision-making and overall mission success. Moreover, the operational procedures for these advanced systems must be meticulously developed and tested, involving extensive simulations and training for astronauts. They need to be well versed in how to handle emergencies, such as an engine failure or a sudden need to change course. And this training must take into account the unique characteristics of the propulsion method being used. The interaction between the crew and the propulsion system, especially in terms of monitoring performance and responding to alerts, is another critical safety aspect that must be addressed. Lastly, the environmental impact of advanced propulsion systems cannot be ignored. For instance, the use of nuclear thermal propulsion raises questions about the potential contamination of the advancements in propulsion technology are set to revolutionize space travel, particularly when it comes to reducing travel times to other planets and moons in our solar system. Traditional chemical rockets, which have powered most of our space missions, rely on burning fuel to create thrust. While effective, these rockets have limitations in terms of speed and efficiency. However, new propulsion technologies, such as ion propulsion, nuclear thermal propulsion, and even concepts like solar sails, are emerging as viable alternatives. Ion propulsion systems, for instance, use electric fields to accelerate ions and produce thrust, allowing for a more efficient use of propellant. These systems can operate continuously for long periods, which means they can gradually build up speed over time, significantly cutting down travel duration. For example, NASA's Dawn spacecraft, which used ion propulsion, was able to reach its destinations in the asteroid belt much quicker than traditional spacecraft would have. Similarly, nuclear thermal propulsion, which uses nuclear reactions to heat a propellant, could potentially double the speed of a spacecraft compared to conventional chemical rockets, enabling missions to Mars to be completed in just a few weeks instead of several months. Moreover, concepts like solar sails use the pressure of sunlight to propel a spacecraft, which could allow for long dimensions with minimal fuel requirements. While still in experimental stages, solar sails have the potential to reach targets like the outer planets and beyond in a fraction of the time it would take with current technology. Such advancements not only promise to shorten travel times, but also to make missions more feasible and cost-effective, opening up new possibilities for exploration. As we look forward to the future of interplanetary travel, these advancements in propulsion technology could mean that missions to the moons of Jupiter, such as Europa, or the surface of Mars, might become routine rather than exceptional. Imagine a future where astronauts can travel to Mars in weeks instead of months, or where robotic missions can reach the distant Kuiper Belt in mere years rather than decades. This rapid advancement not only excites scientists and engineers, but also inspires a new generation of space enthusiasts and dreamers who can envision a human presence on other worlds much sooner than previously thought possible. The implications for space exploration are profound. With shorter travel times, we can expect more frequent missions, which could lead to quicker discoveries and a better understanding of our solar system. With missions planned to launch to asteroids and even sample return missions from Mars, the advancements in propulsion technology are crucial to making these ambitious goals a reality. When discussing the environmental considerations related to propulsion technologies for deep space exploration, it's essential to recognize that the methods we choose to propel spacecraft can have significant impacts, not just on Earth, but also on the celestial bodies we aim to explore. One of the primary concerns revolves around the production and use of propellants. Traditional chemical propulsion systems, which burn fuel to create thrust, can contribute to greenhouse gas emissions and other pollutants on Earth, although their impact is relatively small compared to terrestrial sources. However, as we look toward more advanced propulsion technologies, such as ion drives or solar sails, we must consider their full life cycle, including manufacturing, operation, and eventual disposal. For example, ion propulsion systems utilize electricity to accelerate ions, resulting in very efficient thrust, which is advantageous for long derivative missions. However, the source of that electricity can be a concern. If it comes from fossil fuels, this could negate some of the environmental benefits. In contrast, solar power, which is a clean and renewable energy source, offers a more sustainable option, but it may still have environmental costs associated with the production of solar panels and the materials involved. Moreover, there are environmental considerations related to the potential contamination of other celestial bodies. Planetary protection protocols are essential to prevent Earth microbes from contaminating other planets and moons, as well as to protect Earth from potential extraterrestrial organisms. This means that propulsion technologies must be designed and operated in a way that minimizes the risk of contamination, which can be particularly challenging with advanced propulsion systems that may operate at different temperatures and conditions than those for traditional rockets. The propulsion systems we develop must also consider the long-term sustainability of space exploration. As we venture deeper into space, the potential for space debris becomes a significant concern. If propulsion technologies lead to an increase in defunct satellites or spent rocket stages, this could create hazardous conditions in orbit, affecting not only future missions, but also the environment of low Earth orbit, where many satellites operate. Therefore, it's vital to incorporate debris mitigation strategies into the design of propulsion systems, ensuring that they can be decommissioned or removed safely. Additionally, there is an emerging interest in using in situ resources for propulsion, such as extracting water ice from moons like Europa or Mars to create fuel for return missions. This approach could greatly reduce the amount of propellant that needs to be launched from Earth, thus decreasing the environmental impact of launches. However, the technology to efficiently utilize these resources is still in its infancy, and further research, propulsion systems play a crucial role in the design and operation of spacecraft, influencing not only their weight, but also their fuel efficiency, which is vital for missions that often last for years and travel vast distances. The type of propulsion system selected for a spacecraft can significantly impact its overall mass, as different systems have varying requirements for fuel and engine components. For example, traditional chemical propulsion systems, which are commonly used in rockets, rely on the combustion of fuel and oxidizer to produce thrust. But this process requires a substantial amount of propellant, leading to a heavier spacecraft, especially during launch. The fuel tanks, pumps, and other associated hardware add to the weight, making it a critical consideration during the design phase. In contrast, advanced propulsion systems, such as ion drives or electric propulsion, utilize electricity to accelerate ions, resulting in a much more efficient use of fuel. These systems, while often lighter and requiring less propellant, produce lower thrust, which means they need longer to reach the desired speed, but they can operate for extended periods, making them suitable for deep space missions. The fuel efficiency of a spacecraft is measured in terms of specific impulse, which indicates how effectively a propulsion system converts fuel into thrust. Chemical rockets typically have lower specific impulse compared to electric propulsion systems, meaning that while chemical rockets may provide a quick burst of speed, they consume fuel rapidly, which can limit the range and duration of a mission. Conversely, electric propulsion systems, such as those used by NASA's Dawn spacecraft, can achieve much higher specific impulses, allowing spacecraft to travel farther with less fuel over time. This factor is especially important in missions that involve traveling to distant planets or asteroids, where carrying excess fuel can increase weight and reduce the payload capacity for scientific instruments or the necessary equipment. Moreover, the choice of propulsion system also affects how spacecraft are designed to handle the weight of fuel throughout their journey. As the spacecraft consumes fuel, its weight changes, which can alter its trajectory and maneuverability. Engineers must carefully calculate the initial weight and how the spacecraft's mass will decrease over time as fuel is consumed, ensuring that the vehicle remains balanced and can perform the required maneuvers effectively. Another element to consider is the impact of propulsion systems on spacecraft design and materials. For instance, lighter materials can be used in conjunction with advanced propulsion technologies, allowing for a more efficient overall design. Spacecraft designed for electric propulsion might incorporate lightweight composites and structures that wouldn't be feasible with heavier chemical propulsion systems. International collaboration plays a crucial role in the development of next-generation propulsion technologies, as the challenges associated with advancing space travel are immense, requiring diverse expertise, resources, and perspectives. Various space agencies, such as NASA, the European Space Agency, and others, often come together to share knowledge and research findings, which greatly accelerates innovation. For example, projects like the International Space Station have demonstrated how countries can pool their resources and talents, leading to breakthroughs in materials science, life support systems, and, importantly, propulsion technologies. One significant aspect of this collaboration is the sharing of technological advancements. Countries with different strengths can contribute unique capabilities, such as advanced manufacturing techniques, computational modeling, or experimental testing facilities, which can lead to enhanced propulsion systems. For instance, countries like Russia have a rich history in rocket technology, while the United States has made significant strides in electric propulsion systems. And when these nations collaborate, the result can be a more powerful and efficient propulsion system that benefits all parties involved. Moreover, international partnerships also help to spread the financial burden of research and development. Space missions are incredibly expensive, and by joining forces, countries can share the costs associated with developing new propulsion technologies. This financial collaboration often leads to larger, more ambitious projects, such as the Artemis program, which aims to return humans to the moon and eventually send astronauts to Mars. Through this program, multiple countries are contributing resources, expertise, and technology, which not only enhances the mission's success, but also pushes the boundaries of what is possible in propulsion technology. In addition to cost sharing, international collaboration fosters a spirit of competition and innovation. When countries work together, they often set ambitious goals which can drive technological advancements at an accelerated pace. The urgency to meet these shared objectives can inspire scientists and engineers to think outside the box, resulting in novel propulsion concepts like nuclear thermal propulsion, which could significantly reduce travel time to distant planets. Furthermore, collaboration is essential for regulatory and safety standards in the development of new propulsion technologies. Different countries have different regulations and safety requirements, and by cooperating, they can create harmonized standards that ensure the safe and efficient operation of new propulsion systems. This is particularly important as we move towards more complex missions that involve multiple nations working together in space, such as manned missions to Mars, where reliable and safe propulsion systems will be vital. Finally, international collaboration opens avenues for educational exchange and workforce development. By working together, institutions across the globe can train the next generation of engineers, and partnerships, which combine the strengths of governmental space agencies and private sector companies, can significantly foster innovation in propulsion technologies for deep space exploration. These collaborations create an environment where cutting-edge research, development, and practical application can thrive, leading to the advancement of propulsion systems that are vital for missions beyond Earth's orbit. One of the primary advantages of these partnerships is the pooling of resources, where government funding can support private companies, enabling them to invest in innovative technologies that might be too risky or expensive to pursue independently. For instance, NASA's Collaboration with companies like SpaceX and Blue Origin has led to significant advancements in rocket technology, showcasing how shared goals can drive progress. Moreover, private companies often bring agility and a fresh perspective to the table, allowing for more rapid iteration and testing of new ideas. This is particularly important in the field of propulsion, where traditional methods can be slow to evolve. SpaceX, for example, has developed the Raptor engine, which utilizes methane and liquid oxygen as propellants, representing a shift towards more sustainable fuel sources for future Mars missions. This innovation not only enhances efficiency, but also reduces the logistical challenges of transporting fuel from Earth. Additionally, these partnerships often involve shared knowledge and expertise, where government scientists and engineers collaborate with private sector innovators, leading to a cross-pollination of ideas. Events like the NASA Innovative Advanced Concepts Program encourage small businesses to propose novel propulsion ideas, providing funding and mentorship that can help transform those ideas into viable technologies. Furthermore, competition among private firms, spurred by government contracts and incentives, can lead to breakthroughs in propulsion systems. As companies strive to outperform each other in developing faster, safer, and more efficient engines, the integration of advanced technologies such as artificial intelligence and machine learning into propulsion systems is another area where public partnerships can excel. By working together, agencies can leverage the expertise of private tech companies to analyze massive data sets and optimize propulsion designs, thus enhancing mission planning and vehicle performance. For instance, partnerships focused on electric propulsion technologies like ion thrusters are gaining traction as they promise to provide efficient thrusts for long-duration space missions, making them ideal for deep space exploration. Moreover, these collaborations can help address the funding challenges that often hinder the development of new technologies. Government agencies can provide the initial investment in infrastructure, while private companies can drive innovation and production, creating a sustainable ecosystem that supports long-term research. The Artemis program, aimed at returning humans to the moon and eventually sending them to the moon, particularly in the context of space exploration and travel, is influenced by a variety of economic factors, which play a crucial role in determining the pace and direction of innovation. One of the primary economic factors is the level of investment available for research and development. Government funding, as seen with agencies like NASA and the European Space Agency, can significantly impact the advancement of propulsion technologies. For instance, the allocation of budgetary resources towards projects like the Space Launch System and various Mars missions reflects a commitment to pushing the boundaries of what's possible in propulsion. Moreover, private sector investment is increasingly important, as companies such as SpaceX, Blue Origin, and others seek to develop their own advanced propulsion systems. The competitive landscape encourages innovation, as these companies strive to create more efficient and cost-effective technologies. The economics of scale also play a role. Where the more rockets are built and launched, the lower the cost per launch can become, which in turn fuels further investment and development. Another significant economic factor is the potential for commercial applications of advanced propulsion technologies. As the space industry evolves, the demand for satellite deployment, space tourism, and even asteroid mining grows, creating a financial incentive for companies to invest in improved propulsion systems. The economic viability of these ventures can drive research into technologies like ion propulsion, nuclear thermal propulsion, and electric propulsion, which may offer advantages in terms of efficiency and reduced travel time compared to traditional chemical rockets. Additionally, international competition impacts the development of propulsion technologies. Countries are increasingly recognizing the strategic importance of space capabilities, leading to government-backed initiatives to foster innovation in propulsion. For example, nations like China and Russia are heavily investing in their space programs, which pushes other countries to innovate in order to maintain their competitive edge. The cost of materials and technologies also plays a critical role in the development of advanced propulsion systems. High-performance materials necessary for building engines that can withstand extreme conditions can be expensive, and fluctuations in material costs can impact project budgets. Moreover, the availability of skilled labor and expertise in advanced engineering and technology can influence the success of propulsion projects. In summary, the interplay of government funding, private investment, commercial opportunities, international competition, and the economics surrounding materials and labor all influence how advanced propulsion technologies develop. As these factors continuously evolve, they shape the future of space exploration and the quest for new ways to propel humanity further into the universe. Future propulsion technologies hold the key to human colonization of other celestial bodies, as they promise to overcome the vast distances and challenges presented by space travel. Currently, most space missions rely on chemical propulsion, which, while effective for reaching low Earth orbit, becomes inefficient for traveling to more distant destinations like Mars or the icy moons of Jupiter and Saturn. However, researchers are exploring several advanced propulsion methods that could revolutionize our ability to reach and establish colonies on other worlds. One intriguing option is nuclear thermal propulsion, which uses a nuclear reactor to heat a propellant, such as hydrogen, resulting in greater efficiency than traditional rocket fuels. This technology could significantly reduce travel time to Mars, potentially allowing crews to make the journey in just a few months instead of the many months required with conventional chemical rockets, thus reducing the risks associated with long-duration spaceflight. Additionally, ion propulsion systems, which use electricity to accelerate ions and produce thrust, could provide a more efficient means of propulsion for deep space missions. These systems are capable of operating for extended periods, allowing spacecraft to gradually build up speed and travel further into the solar system, making them ideal candidates for missions to colonize asteroids or the outer planets. Moreover, solar sails, which harness the energy of sunlight for propulsion, present another exciting avenue. By utilizing large reflective sails, spacecraft can be propelled by the pressure of solar radiation, enabling them to travel vast distances without expending propellant, thus making missions to distant celestial bodies more feasible. In addition, researchers are investigating more speculative technologies such as antimatter propulsion, which could theoretically provide immense thrust and drastically reduce travel times across the solar system. By harnessing the energy produced when matter and antimatter collide, this method could enable spacecraft to reach incredible speeds. However, the production and storage of antimatter presents significant engineering challenges that are yet to be overcome. Another exciting concept is the use of fusion propulsion, which would utilize the same reactions that power the stars. Fusion propulsion could offer a long-term, sustainable energy source for interplanetary travel, potentially allowing spacecraft to travel not only to Mars, but also to the outer planets and beyond. As we contemplate human colonization of other celestial bodies, the development of these advanced propulsion technologies is crucial. They will not only make travel more efficient, but also allow for the transportation of necessary supplies, equipment, and personnel to establish habitable environments on other planets or moons. The ability to send larger payloads more frequently will be by the year 2040. The landscape of propulsion systems is expected to undergo significant advancements, driven by the need for more efficient, sustainable, and powerful means of transport, both in space and on Earth. One of the most anticipated milestones is the development of advanced propulsion systems, which utilize electric fields to accelerate ions, creating thrust. Unlike traditional chemical rockets, which rely on burning fuel, ion propulsion offers much higher fuel efficiency and can operate for extended periods, making it ideal for deep space missions. In addition to ion propulsion, the rise of nuclear thermal propulsion systems is on the horizon. These systems use nuclear reactions to heat a propellant, such as hydrogen, and produce thrust. This technology could potentially cut travel times to Mars and beyond, allowing spacecraft to reach their destinations faster than ever before. Moreover, researchers are exploring solar sail technology, which harnesses the pressure of sunlight for propulsion. By unfurling large reflective sails in space, spacecraft can gradually accelerate to high speeds without the need for conventional fuel. This method not only promises to be incredibly efficient, but also opens up new possibilities for long-term missions, enabling exploration of distant celestial bodies. Another exciting development is the potential for electric and hybrid propulsion systems becoming mainstream in aviation, significantly reducing carbon emissions and fuel consumption. Companies are investing in electric aircraft that utilize batteries and electric motors, aiming for commercial viability by 2040, which could revolutionize air travel and transportation logistics. Furthermore, advancements in plasma propulsion systems are anticipated, where superheated gas is expelled to generate thrust. This technology could be beneficial for both space exploration and satellite maneuvering, offering higher efficiency and less environmental impact compared to traditional methods. As we look to the future, the concept of space tethers, which can use the Earth's magnetic field to gain momentum, is also gaining traction. These tethers could allow spacecraft to conserve fuel and extend their range, making them a valuable asset for missions involving satellite deployment and orbital maneuvers. The integration of artificial intelligence into propulsion systems is another milestone on the horizon. AI could optimize flight paths, manage fuel consumption, and predict maintenance needs, improving overall efficiency and safety. As the development of propulsion technologies continues, the collaboration between governmental space agencies, private companies, and academic institutions will play a crucial role in achieving these ambitious goals. Each of these technological milestones points towards a future where space travel is more accessible, efficient, and environmentally friendly, paving the way for humanity to explore the cosmos like never before. Artificial intelligence, often referred to as AI, has the potential to significantly enhance the efficiency and reliability of propulsion systems in space exploration, and this is an exciting area of research that combines advanced technology with the complexities of space travel. One of the primary ways AI can make a difference is through predictive maintenance, where machine learning algorithms analyze data from propulsion systems to predict failures before they occur. By monitoring various parameters such as temperature, pressure, and vibration, AI systems can identify patterns that indicate potential malfunctions, allowing engineers to address these issues proactively rather than reactively, thus improving overall reliability and reducing downtime. In addition to predictive maintenance, AI can optimize propulsion system performance in real time. For instance, during a spacecraft's journey, AI algorithms can adjust thrust levels and fuel consumption based on changing conditions, such as shifts in weight due to fuel usage or unexpected obstacles in the spacecraft's path. This adaptability leads to more efficient fuel usage, which is crucial for long-duration missions, as conserving fuel can extend the range and lifespan of a spacecraft. Moreover, AI's ability to process large volumes of data quickly means that it can simulate various scenarios and determine the most efficient propulsion strategy for a specific mission profile, something that would take humans much longer to compute. Another critical aspect is the design of propulsion systems themselves. AI can aid in the design phase by using generative design techniques, where algorithms explore a vast number of design possibilities and analyze them against performance metrics. This approach can lead to innovative propulsion solutions that might not have been conceived through traditional engineering methods. Furthermore, AI can enhance the reliability of these designs by simulating how they would perform under various space conditions, thus ensuring that when they are built, they are already optimized for efficiency and reliability. AI can also play a role in autonomous decision-making during missions. For instance, If a spacecraft encounters a problem with its propulsion system, AI system could analyze the situation, assess various solutions, and implement corrective actions without waiting for instructions from ground control. This capability is especially valuable in deep space missions, where communication delays can hinder timely responses to issues. By empowering spacecraft with autonomous AI, the reliability of propulsion systems can be greatly enhanced, as the spacecraft can react to problems in real time, ensuring that missions stay on course. Moreover, AI can facilitate the integration of new propulsion technologies, such as electric or ion propulsion systems, which are becoming increasingly important in space exploration. These systems require precise control and management to maximize their effectiveness. AI can development of advanced propulsion technologies for space exploration, while exciting and potentially groundbreaking, raises several ethical considerations that need careful examination. As we push the boundaries of human exploration beyond our planet, the implications of these technologies extend far beyond scientific advancement, touching on moral, environmental, and social dimensions. One primary ethical concern is the potential impact on extraterrestrial environments. For instance, the introduction of Earth-based microorganisms or even human presence could disrupt existing ecosystems on other planets or moons, leading to irreversible changes. Scientists and ethicists alike argue that we have a responsibility to protect these unknown worlds, ensuring that our quest for knowledge does not come at the expense of their natural state. And this is particularly crucial in the context of missions to places like Mars or the icy moons of Jupiter and Saturn, where signs of past or present life could exist. Moreover, there's the issue of resource allocation. Advanced propulsion systems often require significant investment, both financially and in terms of human resources. As we prioritize funding for propulsion technologies that enable interstellar travel or faster journeys within our solar system, we must also consider the opportunity costs associated with such investments. Are we diverting essential resources away from pressing issues on Earth, such as poverty alleviation, climate change mitigation, or healthcare advancements? This brings up questions about equity and access, as the benefits of advanced space exploration may not be evenly distributed, potentially widening the gap between nations with space capabilities and those without. Another ethical aspect revolves around the potential militarization of space. As propulsion technologies advance, the capability to deploy them for military purposes, such as rapid deployment of satellites or even weapon systems, becomes a concern. The ethical implications of this are profound, as space has often been viewed as a domain for peaceful exploration and international cooperation. The risk of escalating tensions between nations, or the possibility of an arms race in space, raises questions about our moral obligations to ensure that space remains a collaborative rather than a combative arena. Furthermore, the notion of human expansion into space introduces a complex ethical dilemma regarding the rights of future generations. As we develop technologies that might allow us to inhabit other planets, we must consider the legacy we leave behind on Earth and beyond. What guidelines should govern our actions as we venture into new worlds? Should we establish principles that prevent the exploitation of extraterrestrial resources, similar to the way we regulate environmental practices on Earth? This is particularly relevant in discussions about asteroids rich in minerals, or the potential mining of other celestial bodies, which could propulsion technologies play a crucial role in determining the sustainability of deep space missions, influencing not only how far we can travel, but also how efficiently we can utilize our resources and how we can minimize our environmental footprint. Traditional chemical propulsion systems, while powerful and reliable, consume a significant amount of fuel, which poses challenges for longer missions where resupplying is not an option. As a result, there has been a growing interest in alternative propulsion methods, such as electric propulsion, which offers much higher efficiency. Electric propulsion systems, like ion thrusters, utilize electricity to accelerate ions and produce thrust, allowing spacecraft to achieve greater speeds with less fuel consumption over extended periods. This means that missions can be designed to reach further destinations, like Mars or even the outer planets, without the need for massive fuel tanks, which would increase the spacecraft's weight and complexity. Moreover, advancements in solar sails, which harness the momentum of sunlight for propulsion, represent another exciting avenue that can enhance mission sustainability. Solar sails can operate without fuel, relying instead on the continuous pressure exerted by sunlight, making them a promising option for long-duration missions that require minimal resources. These sails would allow spacecraft to gradually accelerate over time, reaching impressive speeds without the limitations imposed by traditional fuel sources. In addition to propulsion methods, the sustainability of deep space missions also depends on how we generate and manage energy during these missions. Renewable energy sources such as solar panels are being increasingly utilized to power spacecraft systems and instruments, reducing the reliance on finite resources. For example, the use of radioisotope thermoelectric generators can provide a steady supply of energy for missions exploring distant regions of the solar system, where sunlight may be limited. This approach, combined with advanced energy storage systems, ensures that spacecraft can operate efficiently without depleting their energy supplies too quickly. The development of in-situ resource utilization is another critical factor in enhancing the sustainability of deep space missions. By learning to use local resources found on celestial bodies, such as extracting water from lunar, ice, or Martian soil, future missions could significantly reduce the amount of supplies that need to be launched from Earth. This would not only lower costs, but also lessen the environmental impact of transporting large amounts of material through space, aligning with the principles of sustainability. Moreover, the increasing focus on designing spacecraft with a life cycle approach in mind, where materials are chosen for their recyclability and environmental impact, adds another layer of sustainability. By opting for materials that, in the realm of space exploration, propulsion technologies are vital for advancing our capabilities, and currently there are interesting trends emerging in funding from both governmental and private sectors. Governments around the world, especially those with active space programs, have been increasing their investments in propulsion research, recognizing its importance for future missions, whether they be to the Moon, Mars, or beyond. For example, NASA has allocated substantial budgets toward developing advanced propulsion systems, such as electric propulsion and nuclear thermal propulsion, which promise to significantly reduce travel times and increase payload capacities for deep space missions. The Artemis program, which aims to return humans to the Moon, has also spurred investments, as efficient propulsion technologies are crucial for transporting astronauts and cargo. In addition to governmental funding, private companies have been stepping up their investments in propulsion technologies as well. Companies like SpaceX and Blue Origin are not only developing their rockets, but are also exploring innovative propulsion methods, such as reusable rocket systems, which drastically cut costs and enhance efficiency. Venture capitalists are increasingly interested in funding startups that focus on propulsion innovations, further driving advancements in the field. This trend aligns with a broader shift toward public-public partnerships in space exploration, where government agencies collaborate with private firms to leverage their expertise and resources. Moreover, the rise of small satellite launches has created a niche market for propulsion technologies, with various startups developing new engines tailored for small payloads, which has attracted funding from both private investors and government grants. The U.S. Department of Defense is also investing in propulsion technologies, particularly in the context of national security and satellite deployment, recognizing the strategic importance of advanced propulsion systems in maintaining a technological edge. Internationally, countries like China and India are making significant strides as well, with their governments investing heavily in indigenous propulsion technologies to support their ambitious space programs. This global competition has led to an increase in research funding as nations seek to develop cutting-edge propulsion systems that can support interplanetary travel and advanced satellite operations. In conclusion, the landscape of funding for propulsion technologies is currently vibrant, with both governments and private sectors investing heavily to push the boundaries of what's possible in space travel, indicating a promising future for advancements in propulsion research. Advancements in propulsion technology are opening up exciting new possibilities for humanity's quest to discover extraterrestrial life, as these innovations can significantly reduce travel times to distant celestial bodies, enabling more frequent and efficient exploration missions. For instance, traditional chemical propulsion systems, which have been used for decades, require a considerable amount of fuel and time to reach even the nearest planets in our solar system. However, new propulsion methods, such as ion propulsion and solar sails, are being developed to enhance our capabilities. Ion propulsion, which uses electric fields to accelerate ions, provides a much higher efficiency compared to chemical rockets, allowing spacecraft to travel faster and further while using less fuel. This means that missions can be planned to reach potentially habitable exoplanets more quickly, increasing the likelihood of gathering data in a timely manner. Additionally, concepts like nuclear thermal propulsion or even more speculative technologies such as antimatter propulsion could drastically shorten the travel time to other star systems, which is crucial when considering the vast distances involved. For example, if we could develop a propulsion system that allows us to travel at a significant fraction of the speed of light, we could potentially reach the closest star system, Alpha Centauri, in just a few decades, rather than the thousands of years it would take using current technology. This would facilitate the deployment of more sophisticated probes to investigate the atmospheres of exoplanets, searching for biosignatures or other indicators of life. Moreover, advancements in propulsion technology also enable missions to explore the icy moons of our solar system like Europa and Enceladus, which are believed to harbor subsurface oceans. These missions could include landers or even flybys that can analyze the chemical composition of these bodies, looking for organic materials or other signs of life. The faster and more efficient spacecraft can get to these locations, the more research opportunities we have, potentially leading to groundbreaking discoveries. In addition to speed and efficiency, improvements in propulsion systems can also support larger missions equipped with advanced scientific instruments capable of conducting in-depth analyses of distant worlds. With more powerful propulsion, we can envision sending larger spacecraft equipped with cutting-edge technology to study the atmospheres of distant planets, analyze surface materials, and even return samples to Earth for further examination.